Welcome to this explainer. Imagine millions of passengers traveling every single day on one of the world's largest railway networks, Indian Railways. It's this sprawling, incredibly complex web of moving metals, signals, and switches. But what is the invisible heartbeat actually keeping this giant system alive, coordinated, and most importantly, safe? Well, today, we're decoding a massive engineering marvel that works entirely behind the scenes.
So think about the stakes for a second. What actually happens when the power grid fails on a network this massive? I mean, even for a brief moment. If a blackout hits, signal lamps go dark, relay communications just stop, and trains are forced to halt or, terrifyingly, run blind. Historically, trying to manage power across thousands of remote stations was an absolute logistical nightmare.
Back in the day, the setup was honestly a chaotic mess. Stations had to rely on multiple batteries, all with totally different voltages and amp hours, which meant a confusing jumble of different chargers. And whenever the grid dropped, bam! Loud, fuel-guzzling diesel generators had to kick in immediately just to keep train movements going. But then came the game changer, the Integrated Power Supply, or IPS. Instead of all that chaos, it uses one elegant, centralized 110-volt battery bank. It provides clean, continuous power to the signal lamps and relays, no instant panic for a diesel generator required.
Okay, let's dive into this. Here's our roadmap. 1. The railway power problem. 2. The IPS solution. 3. Inside the power rack. 4. Smart switching and safety. And 5. Keeping the system alive.
All right, kicking things off with part 1, the railway power problem.
Now, this technology didn't just appear out of thin air, right? The initial concept for the IPS was actually proposed by the Research Design and Standards Organization, or RDSO, way back in 1996. By 1999, they rolled out the first generation using thyristor-based chargers and transformer rectifier sets. But as we know, technology moves incredibly fast. They quickly leveled up to a second generation, introducing DC-DC converters to drastically boost both efficiency and reliability. And today, we're on the third generation. This version uses highly advanced switch mode power supply, or SMPS technology, and it even packs advanced surge protection devices to shield the whole setup from literal lightning strikes.
Which brings us to Section 2, the IPS solution. You can really think of the IPS as the ultimate electrical Swiss Army knife. It's a complete, all-in-one power solution that meticulously shapes messy grid power for every specific railway need. How? By integrating 4 completely different power conversions into one single system. It rectifies alternating current into direct current, it chops high-voltage DC down into lower-voltage DC, it inverts DC back into AC, and it steps AC voltages up or down. Seriously, it does the whole shebang.
And a huge player in actually bringing this RDSO concept to life has been Amara Raja. They've been operating since 1987, and they manufactured the very first prototype IPS systems back in 1999. They put these things through the ringer, subjecting them to extreme simulated field conditions just to make absolutely sure they can handle the harsh everyday realities of the Indian railway environment.
Moving right along to Section 3, inside the power rack.
Now, what's really interesting here is the sheer modular complexity of the full SMPS-based rack. Honestly, it looks a lot like a high-end server farm. But every single one of those individual panels and pull-out trays serves a highly specific, coordinated purpose to guarantee uninterrupted power. Let's translate some of this alphabet soup and break down what these modules actually do.
We can basically think of these parts as the organs of the system. First up, the SMPS panel takes your standard 230-volt AC input and converts it into a stable 110-volt DC just to charge the battery bank. Next, the DC distribution panel, or DC-DP, takes that 110-volt DC and chops it way down to anywhere between 6 and 60 volts. That feeds delicate signaling gears like relays and data loggers. On the flip side, the AC distribution panel, or ACDP, does the exact opposite. It inverts the 110-volt DC back into 230-volt AC for the signal lamps. And finally, the LPD box acts as the system's immune system, providing absolutely crucial Class B and C lightning and surge protection.
If we look right inside the AC distribution panel, you'll find these heavy-duty step-down transformers. They take that 230-volt AC from the inverters and step it down to a constant 110-volt AC supply. And that is the exact power feed that keeps those vital signal lamps glowing brightly and track circuits functioning, totally regardless of what the main power grid is doing.
All right, Section 4, smart switching and safety.
So the absolutely crucial point here is this tiny measurement, under 60 milliseconds. The system features a microcontroller-based static auto changeover switch. If an inverter fails, this static switch swaps over to a backup power source in less than 60 milliseconds. That is literally faster than the blink of an eye. It's so incredibly fast that a signal lamp out on the tracks won't even flicker.
Here's that fail-safe brain actually doing its thing. The microcontroller constantly monitors the system using a logic table. If inverter 1 is healthy, it routes power straight through static switch 1. If inverter 1 fails but inverter 2 is healthy, boom, it instantly triggers switch 2. Now, if both inverters completely fail, the logic table tells it to immediately trigger switch 3, which pulls power from a bypass constant voltage transformer. It's just this rapid-fire decision matrix, making sure the signal always has power.
And the hardware making those protections possible is the silicon-controlled rectifier undervoltage and overvoltage circuit board. Try saying that 3 times fast. Basically, it acts as a physical shield for the entire IPS. If the grid voltage drops below 150 volts or spikes dangerously above 275 volts, this sensing circuit instantly disconnects the mains to protect all those sensitive modules inside.
Finally, let's wrap up with Section 5, keeping the system alive.
Think of the ASM status monitoring panel as the IPS dashboard. This panel is wall-mounted right inside the station master's room. It basically allows the human operators to see exactly what that hidden power rack is doing at a single glance, relying on a simple LED bar graph and some very critical audio-visual alarms. And these alarms are designed in escalating thresholds to stop a disaster before it starts. If the battery discharges to 50%, an audio alarm sounds and the start generator light glows. Drops to 60%, the warning intensifies, prompting an emergency start. If it reaches a critical 70% discharge, hitting exactly 105 volts, a forced system shutdown kicks in to prevent the battery from dying completely. And what if an individual module fails? A bright red Call S&T staff light immediately tells the station master it's time to call in the signal and telecommunication engineers right away.
Now, when the engineers actually arrive, the stakes are incredibly high. They have to follow a very strict maintenance manual to prevent accidents. First, keep the input circuit breakers on. Next, regularly check that the earth pit resistance is under 2 ohms, otherwise that lightning protection might fail. Clean modules only with compressed air or soft cloths. They are strictly warned to never use makeshift wire fuses. And crucially, if the system shuts down, they must absolutely never restart it without identifying the root cause first. The sheer scale of coordination happening inside these metal cabinets is honestly mind-boggling. It shapes raw grid power, filters out lightning strikes, and swaps failing circuits in milliseconds. So the next time you're on a train and you see a green railway signal shining clearly in the distance, ask yourself, will you picture the lightning-fast, fail-safe robotic brain working tirelessly in the shadows to keep you safe? Thanks for joining me on this explainer, and as always, keep staying curious.